ओके डियर स्टूडेंट्स, अब चलते हैं एक नया वीडियो में अल्टरनेटिंग करंट 17। इसमें विल कैलकुलेट द एनर्जी स्टोर्ड इन एन इंडक्टर एंड व्हाट इज एन इंडक्टर आई हैव एक्सप्लेन्ड यू बिफोर. An inductor is a conducting wire in the form of a coil. The L was called its self-inductance, and I have also explained you the meaning of L. Let me explain and once more then come back here, come back to the original derivation. In electromagnetism, this property, self-inductance, was acting as the electrical inertia. Like in kinematics, suppose you have a toy car, small m, it is at rest. To change its state from rest to motion, because its mass is less, you require less force. Supposing there is a truck, a lorry, the mass of this is much more than this. This is also at rest. Now to bring this into motion, you need a large force. This force is more than this. Similarly, if this is already moving at say 10 meter per second, and this is also moving at 10 meter per second, and you want to decrease this speed by applying force, then you also require a small force. Here also, if this is already moving, you require a larger force as compared to the force to reduce its speed. Means whenever you want to change the state, either from state of rest to state of motion, or from state of motion to state of rest, more the mass, more is the force, less the mass, less is the force. That inherent property is called inertia. More the mass, more is the inertia. Less the mass, less is the inertia. So here similarly, what this was doing, as when you were alternating, voltage was applied and there was alternating current, and the alternating current was lagging behind the EMF, and whenever the current was changing, this property, inductance, was opposing it. You can compare here. It is changing from rest to motion. The mass is opposing. Here in this case, if it is in motion, you want to bring back to rest or reduce the speed, then less force is required here, more force is required here. It does the same thing here in electrical circuit. If the current is increasing, it tries to oppose it. If the current is decreasing, it also tries to oppose that. By developing an EMF, it was derived in previous lessons as minus L di by dt. This is called back EMF. Now, let me explain this diagram and then come back to the original derivation of this lesson. All these things I'm explaining, this you don't have to write while writing this theory part. This is for your explanation only. Now look at this expression for EMF developed by the self-inductor when the current is growing or when the current is decreasing. Now there is a derivative of term di. If I is changing, then only di by dt has a value, so there is back EMF. I is constant, derivative of a constant is 0 into L is 0, so opposing EMF is 0. So let me tell you where it is, where this EMF is 0. Now look at this diagram. This red one indicates the alternating voltage is equal to E naught sin omega t. This point is 0. Now this is equal to your 2 pi. Half of that here is equal to your pi. Half of this is equal to, point is pi by 2. This is pi by 2, pi by 2, pi by 2. This is your 3 pi by 2. Now this black line is the alternating current I is equal to I naught sin omega t minus pi by 2. Now look, when EMF is maximum, the current is 0. Now, when the EMF is 0, the current is maximum. Or you can say, now let me explain it from the current point of view. When the current is 0, the EMF is maximum. So, when the EMF is 0, the current is maximum and the process continues, right? Now, from here to here is also pi by 2. So, this point will be 2 pi plus pi by 2, that is equal to 1, 2, 3, 4, 5. 5 pi by 2. So, this indicates, right? Now, look, in which case this di by dt term, at what point this di by dt will be 0, means there is no back EMF. Now, look at the point here. Here, the current is maximum, that is I naught. So, your I becomes maximum, derivative of maximum, a constant is 0. So, here there is no back EMF, and at this point also there is no back EMF, right? Now, let us then come back to the derivation part of it, which is very simple. Now, look, let L is equal to self-inductance of an inductor, which I just explained. This is the property of a coil due to which whenever the current was growing in the circuit containing an inductance L, it was opposing by creating an EMF minus L di by dt. The negative sign only indicates it opposes. In previous lessons, I had explained, I had used formula small e for this. It's alright, you can use capital E also, no problem. Now, AC is applied, means alternating current is applied across the inductor. So, the current grows from 0 to maximum, then from maximum to 0, then from 0 to maximum on the other side, then from maximum to 0, right? That is how the current, alternating current. So, as explained in earlier lessons, there is a back EMF. There is a back EMF minus L di by dt. Its magnitude is this much. This negative sign only indicates some concept that it is opposing, right? This is called your back EMF, which opposes the current. When the current is growing or increasing or decreasing, but not here, not at this black line represents the current, I is equal to I naught sin omega t minus pi by 2, but not at this point, not that. Here the current is maximum, I naught. Here also the current is maximum in the opposite direction, I naught. Maximum, that is a constant. Here that is a constant, means di by dt is equal to 0. And the meaning of derivative as you know in mathematics, it gives you nothing but the slope. The slope of this line here is a 0. The slope of this curve here also a 0. So at these 2 points, there is no back EMF. This is what you are not required to write. While if you are asked to find what is energy stored in an inductor, you have to only write these parts. Not the explanation part. The explanation part is for your own understanding of physics better, right? So now let us proceed further. So to maintain the current I at some instant t, some work has to be done because it is opposing. So some work has to be done. Let that small d work, dw is the small work done in time dt. So dw by dt, work divided by time. Work divided by time is power. And look at here, is voltage into current. Power we also derived in current electricity is VI. V is same thing as E, so EI. Now let us explain further. So dw by dt, this is your back EMF. So that is, I am taking the magnitude part of it, L di by dt, because the negative sign only indicates it opposes. Since it is opposing the growth of current or the decay of current, some work has to be done externally to maintain the current. So for E I put L di by dt, I remains the same, dt cancels. So So I am left with dw is equal to Li di. So this is the small work done when the change in current is equal to di. So what will be dw is equal to Li di. So the total work done. So the total work done to establish the current I will be integration of this dw. Will be integration of this w. So your total work done w is equal to integration of dw. For dw I put Li di. L is a constant that is taken out to maintain the current at I. So the limit of the integration, since I am integrating I with respect to I, so the limit will be the limits of the current from 0 to I. So this becomes I square by 2 in the limit from 0 to I. So your work done is equal to, L I square by 2 minus 0, that is half Li square. So this work done to maintain the current I is nothing but the energies of the inductor. It is called the magnetic potential energy of the inductor. Symbol is UB. W is half Li square. How do you say magnetic? Because we have already seen in previous lessons for a coil carrying current, an inductor carrying current, if from this side the direction of current was anti-clockwise, this was behaving as a north pole, this side it will be clockwise, south pole, means the whole coil was behaving as a magnet. These were its magnetic lines of force, originating from here, moving like this, passing through the magnet at south. These are continuous lines. So it was behaving as a magnet. More lines of force are concentrated here and here. If you hold a unit area here, the flux will be more. If you hold it here, the flux will be more. If you hold the area here, the lines of force passing through this normally will be less. Here it will be less. This is what I wanted to brush off your previous knowledge, which I explained in previous lessons. So this is the energy stored in the inductor in its magnetic field, because when current is flowing, it is behaving as a magnet, right? Okay. Now then, coming back to a small numerical, a 1.5 millihenry inductor in LC circuit stores a maximum energy 17 microjoule. What is the peak current? So what is given? L is given 1 millihenry, 1.5 into 10 to the power minus 3 Henry. To convert milli to Henry, I have to multiply this. Then maximum. This is maximum if I is equal to maximum. I maximum is called I naught. So U maximum, which is given as 17 microjoule, will be half L I maximum square, because it is given maximum energy. And the energy equation is half Li square, which we just derived. Half is constant, L is constant. So if I is maximum, then this will be maximum. And I maximum is called I naught. So half L I naught square is equal to 17 microjoule, that is 17 to 10 to the power minus 6 joule. Then what is to find out I naught? So just substitute half Li square is 17 into 10 to the power minus 6 joule. So half L is given, I naught is to be found out is 17 into 10 to the power minus 6. So I naught is equal to, this 2 comes here, this 1.5 10 to the power minus 3 comes to this side, it's divided, square root of that, this comes out to be 0.15 ampere. So this is the current, maximum current, when the maximum energy is equal to 17 microjoule in an inductor having value 1.5 millihenry.